Akim, thank you for inviting me, and thank you for this really nice conference. I think I'm the token The Hague speaker because we are really just down there. I'll be reporting from my specific rabbit hole in which I've dug really deep and interesting tunnels. I don't get many visitors, so I love to show you around. So the talk, there's a lot of talk in today about letters and numbers and cataloging, indexing. And Akim asked me specifically to say, well, there are certain conditions under which letters are numbers. Not just look like a number or represent one in some sort of mathematical statement, but really perform arithmetic. So I will try to show you how this works and why this might be useful in contemporary type design, and just what tool building and a curious type designer can do with it. I also understand that this is the last talk and everybody's tired, so letters and numbers. What I'm not going to talk about is all of the Google image searches I did. You can imagine that letters as part of cryptography have something to do with this, and if you Google cryptography, you get things like this, which is amazing, because this is exactly how cryptography works. I'm also not going to talk about numerology, which is attaching meaning to letters and numbers, and this is one of the better ones. I also like that in order to do numerology, you need OCR typefaces, and there will be sparks, but your eyes will be blank. I'm also not going to talk about ciphers and letters, which was this really weird game show in Holland, and I was thinking there has to be at least one pop culture reference in this. I'll spare you the video that I found for this. What I do want to talk about is different digital letters. So I'm going to avoid the symbols, the cryptology, the numerology, the philosophy, the math, and anything to do with linguistics, in which symbols represent multiple things at once. I'm going to talk about digital letters, and specifically letters as characters, letters as shapes, and letters as mathematical objects. You're in for a fun ride. It's like, oh yes, arithmetic, of course. What is a number? Now, there's also a philosophical discussion there, and maybe Akim will discuss this at some other conference, but I'm hastily avoiding any of that by skipping straight to the math and the things that I find comfortable. So let's just assume that any object, anything that follows the rules of arithmetic could be considered a number, right? It's very easy to reach agreement on this right now because we all just want to go home, but at least, you know, if you can do arithmetic with a thing, maybe it sort of looks like a number. Do we know the rules of arithmetic? Anybody sort of like want to? There's the of course now, just to bring this back into memory because we are all ready to say this, we're just too shy. Associative law for addition, so if you add A plus B and then C, you will get the same result if you have A and you add B and C together, and you do these things. The same for multiplying, A times B, and then later times C is the same as A times the product of B and C. You know all this. Mathematicians come up with difficult names. I had to get this from the Wikipedia page because obviously I don't know these things, but I do know if you add 1 plus 3, you will expect the same result than if you add 3 plus 1. So. Then I thought, okay, well, this is the first thing. This is characters as a semantic number. This is not my field. Let me breathe. This is not my field, but I just needed to include this because there might be some funny things in there. Letters are marks on the surface, right? And once they exist, they can be indexed and cataloged and discussed. And this indexing is maybe what we've seen in some of the talks today. And it's a very serious and academic activity. It enables the encoding of writing systems, past and present, and it let us record language into a series of bytes, because that's what we have to do. So this is the world of Unicode. It makes sure that the messages we send are the messages our friends receive, and that, God forbid, it will remain readable and searchable in the future, because all of our messages, you know, Google in 20 years. So, there is a YouTube series called Computer File. This is from the same authors as the YouTube series Number File by Brady Haran. And it is a series of short introductions into the history of computing, but also basically, you know, this is from the University of Nottingham. They interview mathematicians and they come up with really interesting stuff, just how math works. And I understand nothing of it. I'm just a mathematical groupie, but I really love to see people talk about these things and things like Graham's number or infinities or Hilbert spaces. All of that stuff is amazing. So one of the episodes you need to look for is a computer file episode on UTF-8, which is sort of the nitty-gritty stuff on how Unicode is encoded in sequences of bytes. And one of the early stuff that was going on, so there was telex code, and there was 4-bit, and then it became ASCII. And so if you have a lowercase a, and it's represented in hexadecimal 61 or decimal 97, you notice, obviously, and you subtract capital A, which is hexadecimal 41, you will get space, which is kind of cool. So for the first ASCII characters, anything that has casing, if you add hexadecimal 20 to the capital, you will get the lowercase. Does this work? Do these relationships happen in other parts of Unicode? I thought, let's investigate. So, if I take a smiley face with party hat and I subtract a neutral face, do I get party? Right? No, I get 15389. I do not get party, I get combining small letter a. Which is not nearly as fun and doesn't have any meaning. If you want to play with this, Unicode is fully supported in Python 3. So all Python string objects are fully Unicode. You can put all the emoji in there. You can put all of the Greek and the ancient stuff and the new stuff and the hieroglyphics. You can put in Python and you can do math with it. So here it says, get the ordinal value of the string A, and then get the ordinal value of the string of lowercase a, and then print b minus a, we get 32, which is hex 20, which is space. And of course, for instance, like the opposite of ordinal would be changes into character. So the ordinal of C plus the difference of capital A minus, or is it like the B minus A? Anyway, I can get the numeric difference between A and B and add it to C, and now I get a lowercase c. That's fun. It's probably also the places where this works. I'm imagining there might be some sort of Unicode numerology where, what was going on with WebDing, so you add the American flag and you subtract an airplane, and then you add the word, I don't know. There might be lots of conspiracy stuff in there. Anyway. This is a quick side move. I'm just going to advertise small, completely unfunded but super useful open source projects. Open source being it's free, which means that nobody gets paid for doing this. A project called Glyph Name Formatter that I've been doing for a couple of years now with Frederik Berlaan. And here we take all of the character descriptions from the Unicode list and turn them into sort of practical glyph names. If you're doing type design, you don't want to have the hexadecimal value. You also don't need the really long, small Latin letter A with diresis below or whatever. All of those names. You want to have sort of a useful name. So when I say the entire Unicode, I am lying. Out of this morning I saw 137,928 characters in Unicode 12. The glyph name formatter only generates a paltry 11,075. So we're only covering 12.4%, but all of these glyph names are available in the tools so you want to use them for. I know Glyphs has its own list, and FontLab has its own list. This is what we do for RoboFont. Some other people use it too. So if you want to have a look at the name, if you want to look at the list, if you want to participate, if you want to comment, all of your participation is welcome. But that's not what I wanted to talk about. This is certainly not what I know about. This is not my rabbit hole. What about shapes as numbers? What about geometry? So we can digitize the shape of a letter. This is the more comfortable world of geometry. It's like mathematical descriptions of curves, cubic, quadratic, maybe Euler, spirals, God knows what we were thinking of, straights, and then these shapes are used in rasterization. The digital shape of a letter we call a glyph. You know this. A glyph is also often associated with a Unicode value, but it doesn't have to be. So we try to make more glyphs because there might be different drawings of the same Unicode value. A different glyph object itself contains a small hierarchy of data, again, mostly geometric, contours, segments, points, information about smoothness, horizontal, vertical advance width, anchors, guidelines, background images, and references to other glyphs, notes, and a bunch of arbitrary data. To make sense of this, if you want to work with this, we have a really useful package called Font Parts. It's the successor to RoboFab. This is what was part of we had running in FontLab, and before that in other editors. But these are Python objects. There's a font object, and there's a lib font info with stuff on a font level, so vertical metrics, for instance, kerning, feature code, and within a font there are layers. Within a layer there's a glyph, and glyph has anchors, components, images, guidelines, contours has points, contours has Bezier points, and contours has segments. So this is sort of a hierarchical structure of how you can drill down from a font into actual points, coordinates. So a glyph has contours, contour has segments, segment has points. Each point has a coordinate, an x and a y, as Akim showed. But components and anchors also have coordinates. So this is what we do. Then we get into this. All of this is lovely, and we want to make these fonts, and we want to make variable fonts, and we want to make interpolating things, and then it gets tricky because we need tools to do this, and yet somehow, these tools exist or they don't exist. The specifications might be new. We might want to do things that have not been done before. So we have to start thinking about how to make these tools. And one of the things that happened a long time ago is that if you look at a glyph object not just as a container of numbers, but as an actual object that can perform arithmetic. So which means that you would have a lowercase a, and you can add another lowercase a. And this would not just be two shapes stacked on top of each other, or a string with two a's in a row, but these would be, if the outlines match up and the points match up, the coordinates would add up. So it's basically sort of a composite object that behaves in a mathematical way. Python has some methods for this. So if you add under, and like sub, and mul, and div, if you add these methods to your object, you can make an object perform in arithmetic. You can have your object do something while it gets added to something else, or it gets multiplied. This started, I think the oldest stuff I could find when we were doing this is like a really old module, and I've always loved it, and I've always cherished it. Had many positive feelings about the stuff that this font math package had let us do. Going back to 2003, I realized that digital archiving is not what I imagined it to be. I could find no emails. I could find one file, and that was also already not the first version. My friend Tel Lemming, who worked on this, had, I think, 1 or 2 text files that came out of some sort of a versioning thing. So I think 2003, that's already the smoky horizon where beyond which all of my data is gone. Apropos of nothing, I think it was just an interesting thing to realize. The early stuff, I think, was done with Frederik de Blazer, and then Just van Rossum and Tel Lemming. And we started playing with this idea of what happens if you actually start doing math with glyph objects. So what does it mean? We're not adding the geometry, basically, what you would say as Boolean glyph objects, where you say, well, you just add the outlines. We're not adding Unicode values, because that doesn't work either, we've seen. But under very specific conditions, we can, when all of the data is present in both glyphs, we can add them up, and we can subtract them, and we can multiply, and we can divide them. Basically, we can apply mathematical operations to the coordinates, and then make a new glyph object and return it. So, these are generated with Drawbot. Here's my 2 happy test subjects from a typeface called Mutator Sans, which is also open source. I keep it around for tricks like this. It's never going to be finished. It certainly doesn't have a lowercase, but for stuff like this, it's fine. Bold, condensed capital letter R, and a wide, bold capital letter R. The condensed one I call A, and the wide one I call B. And if I go to a random point, basically you can see it's somewhere in the tail. This one is at 11 83, and this one is 672 to 11. But they're both at the same index, and they're both at the same place in the glyph, and the glyphs have the same number of coordinates and the same number of points. So I can do something with that. And here's another one. So each point in one glyph has a partner in the other, which means I can subtract them. I can say, okay, well, what do I get? What happens with this object if I take the condensed one and then subtract the white one? So this would be 365 minus 771. You get minus 46. You know this? 548 minus 113 is 35. So this shape in red, this thing, is the visual result of two subtracted glyphs. Basically, it's literally, the shape represents the difference between these two shapes. So you can see that these letters don't differ that much in height. There's something going on in the width, but this doesn't change, but this doesn't change. So the counter changes most. You will see that there's a lot of stuff happening in the counter. If you know how to read the shape, there's a meaning to it. Other arithmetic that we need to do, we need to be able to multiply. So I take my object A and I multiply it by a half. And what do I get? Basically, all of the coordinates get scaled, and we get the tiny red one. 365 is divided by 2, becomes 182.5. So that makes sense. I can scale a glyph, and I can multiply it with 2, so then it just becomes bigger. So multiplying with a number basically represents a scale, whereas subtraction and addition gets into these really weird intermediate shapes, these weird wonky things at the corner. This formula, if I take the white one and I add half of the difference between the condensed one and the white one, this becomes an interpolation. So there's the orange one and there's the other one. You see that this coordinate is right in the middle between those two. I know you can interpolate. I know we can write a function where it takes one glyph and it takes another glyph, and then we can cycle through all of the points and come up with this numerically. The really interesting thing about writing it like this is that formula, the white text at the top, that is the actual code that caused the interpolation. The object is represented by the name, and just writing that causes that calculation to happen. And here's a similar one, there's another one. So it's more towards the purple one. So that means that we can experiment with this, and we can maybe have some rules. And maybe we can do some layout or make some sketches of how these calculations work. At the most minimal view, an interpolation has like one glyph and the other glyph. Maybe I can put one in the middle. So first we go from A to B, and then we go from B to C, which would be sort of like one stop in the middle, one station in the middle. I can give them names. I say, well, one of them is the default, and then if I move along the blue axis, I get the value 1, then this is the first stop. Or I say, I put the default in the middle, and then if I move -1 on the blue axis, I get to the left, and if I move to plus, I get to the right. I can give coordinates. I can sort of start mapping out what the space would be like. I can add another vector. I say, well, here's a blue one. If I start at the default and I go on the blue axis, I get this. But if I go along the purple axis, I get something else. And by doing that, by saying there's a new dimension, there's a new thing along which I can put values, I also create a new point in the gray dot. It says, okay, well, what happens when you get to this combination? You can also do this with the 3-axis. You get 2 open points, or you can even do it with a cube. So this will be the default to one axis, another one, and another one. But I also get 1, 2, 3, 4 superpositions of what the changes in these masters would do. Font math enables all of this. With font math, you can build open-ended interpolation systems. The interpolation depends on the shapes that you need and what, for the design that you're making, for the typeface that you're making, what variation is needed and what how that should develop. This should not be part of code. How your design is fit, how your design is expressed in different axes. It should not be a tool that says, oh, here's one slider for this axis and here's a slider for the other axis. The design should determine which axis you need, and the mathematical model should build itself, and font math lets you do that. So there's a certain grammar to these design spaces. There are rules for construction. and not all combinations make sense. One on the left, there's a default, there's a purple axis, and then there's a blue axis but doesn't have any master, and then there's sort of an off-axis master that is not connected to anything. That won't work. Or the one in the middle, we have two masters, one on the blue axis, one on the purple axis, but there's no default. And here's one default, and there's an off-axis master, but there's no... So there are certain limitations to it. Do we want this to make sense? Maybe. Can you write a theoretical treatise about it? Certainly. Will it help you make variable fonts? Maybe not so much. So here's the thing about variable fonts and the math that went into that. When Mike Reed started working on what would become GX at Apple, I think, 1991 maybe, 1992, he was basically abusing the hints system to move points around. He said, well, we can actually do some interesting math with it. GX came and went, Steve Jobs came and went, and then so 2015, 2014, a couple of people started thinking, well, actually for the web, it would be nice if we can have sort of variable interpolating systems. Adam Twardog was involved, and B.SVBot was one of the big forces behind it to get this going. So all of a sudden, this old mathematical model of GX became interesting again. And I kind of knew how it worked because it was the model that we had been using in font math for years. What happens? It's nice when everything lines up nicely. It's nice when you have the bold and the white and the condensed and the light and everything is nicely sort of cubed and every master has a matching master somewhere else. So what happens if you need to get an orange master somewhere in the middle? Like all of the extremes are nice, but this thing in the middle is terrible. You need to fix this. You want to put that shape in there. You can still calculate. It sort of becomes a pyramid. You can say, well, if you get closer towards the orange point, that master is factored in more. And if you get further away from it, it's reduced again. So at the edges, it would be the old interpolation. And then when you get closer in the middle, you would at some point see that thing. Great. But what happens if you want to have two masters in the middle? There's no history for this. There's no precedent. There's no way of actually saying how this should be done because we've never done this before. Nowhere in type design was this problem ever relevant. But now we have the math and the variable font stuff is built into all of our phones and devices. And we should definitely start thinking about how to make good fonts for this. So mutator math, the thing that I made for font math in 2003, and varlib, the code that now determines how these masters are interpreted in font tools, which is the library that Google uses to make things like Noto, have slightly different ideas about this. Not because I got it wrong or because Google got it wrong, it's just that there are different ways of solving this because there isn't a single way to solve it. I think font tools, the varlib model is nicer. It's the one that Bedad wrote after looking at mine. I was really nervous. I sort of make this thing and then Bedad comes and checks it. It's like somebody's checking my math homework. Of course I'm wrong. But his model is nicer, but it fails to implement extrapolation. And extrapolation is really useful for type design. So in my tools, I'm then again juggling both of them. There's mutator math, you want to do extrapolation, and there's varlib if you want to do the other things, or want to go to a variable font. Then I got into this thing. This is such an interesting field for research. I mean, this animation shows 4 masters at the corner. So it's a 2-dimensional system. You can imagine that these gray dots, it's like bold condensed, bold wide, or whatever, it doesn't really matter. And then we have 3 intermediate masters, because in this system that was necessary. We needed to fix something in the S, and there was some kinking going on, and there was no other way of doing it. So for whatever reason, these 3 masters are in the 2-dimensional plane. So there's G, there's E, F, and G. The number behind it is how varlib sorts it. So varlib has a particular algorithm of building this space, of trying to make sense of these masters. So F and G are in fixed place, and E I move around, just to show that the decision where you want to put the 3rd intermediate is relevant, because if it's in this lower half, you will see that the color of this, the blue thing, the purple, this one, is the reach of this master. It's like the places in the design space where you will be able to see the effects of what you do. This is a big deal. this is a full master. These are all of the glyphs you're drawing. Right? These are hours of your life. You want these things to matter. You want these things to have an effect and be visible in various places. But you see how different that is once it goes from, where is it? So it goes from here to here. You see that all of a sudden the block where this is visible changes rapidly. So if you want to move your master in this place, you could see it maybe from the bold to the thin, and you move it 1 unit to the left, you might only see it from the narrow to the narrow to the wide. For a type designer, these are big deals. For an engineer, this is not a big deal. You think, oh, what? You just make this, and whatever happens, happens. But as a designer, I need to be sure that the things I draw have an effect, and these effects happen where I need them. This also means that if you want to make a subset of your variable font, so you put 100 masters in and 27 axes, and because this is the web, you say, oh, we'll just make a subset, we'll just knock some of the axes out and take some of the spaces out. All of a sudden, this is no longer possible, because the effects will change, the design space will change, and the results of the masters will change. You cannot subset a variable font like this. Anyway, almost there. So, interpolation and the way that variable fonts work basically means you start with a default and then you add a factor, a certain amount, a fraction of this difference. Now this crumpled looking letter that we saw on the left. And you do this for all of the masters that you add. And you do this, and the game is then to calculate what these factors are. And then that's where these math models come in, and that's where the Voorhout thing comes in. But basically, this is the function. Interpolation has become a simple list of things to multiply and add up without writing any special code for it, because the glyphs themselves are doing the math. Then I made some funny stuff. So this is the same for glyphs. This is the default is in blue, if you can see it. And then there's the light blue one, and then there's the orange one and the red one. These are the three factors that are sort of adding up and dancing around to make the bold white or whatever the yellow result is. And I think it's really nice to actually have all of these weird crumpled components that are part of the math that you don't usually see, but now as dancing around on the screen. And here's one with everything. This is not meant to illuminate or cause panic. This is what happens in a straightforward two-dimensional four-master interpolation, and the interpolation is sort of hovering between that, and you get all of these points dancing around. The numbers that you see are the coordinates of a single point that's selected, and then all of the wild stuff near the zero. It means that you can define these interpolations with any number of masters and any number of dimensions as a list of items to multiply and add. I know. So, font math available for GitHub Robotools Font Math. It's a modest but very powerful package. There's very little documentation, but basically, if you have font parts or RoboFont, you can say, my glyph to math glyph, and you will have the math glyph. You can do all the math, and then reverse, make it go back into RoboFont or your editor. There's font parts if you want to have a look on GitHub, and there's glyph name formatter on GitHub, and there's a skateboard if you really want to see what was going on. And I'm happy to say that this was 24 minutes, and I'm done. Thank you very much.